Okay, everyone. So I talked about how I would bring this up today, and that is in terms of AC motors and their power factor and their efficiency. Now, efficiency is certainly something that we should remember from back in the first part of the course where we're looking at our P in and P out values and P losses and how that results in what we can call the efficiency. And then now we can bring in the power factor of the motor when it comes to its connection in an AC circuit and the coils and inductors that make up the load part of the motor, and how that is going to be giving us a specific power factor with some QL or inductive VARs in it. So remember, AC loads are rated by VAs so that instead of watts, so that we can design or predict the amount of current that will be drawn from a source, which will be determined by the VA value, not by the power value. We're going to have more current coming from a load with a poor power factor that includes more QL, and so we have to rate it as its VA. And then we'll be able to determine things like that when it comes to design or connecting it to a source. So one thing to probably mention here is when it comes to the power factor of a motor, that's where you're looking at the VA value when the motor is a load. So that means the motor is a load to the electric circuit, right? So when it comes to this circuit, this electric circuit, the motor is the load, the electric load, right? That electric load is rated as its VA value. And then, of course, within the VA value and the power factor, you would have a power triangle, right? So as far as the motor goes, you would have a motor power triangle, where in the motor's power triangle, you're going to have P, you're going to have QL, and you're going to have the overall VA or S value of the motor, where you're going to have an angle here, theta, which is going to yield your power factor, right? So that's going to give your VA and a power factor when you're talking about the motor as the load in this electric circuit. But remember, there's another circuit, essentially the mechanical circuit, of where the motor is the source to the mechanical circuit. And when we look at the mechanical circuit, it's entirely real power. It's entirely all watts or horsepower. So if we were to go over here and we were to start by looking at the real or true or average power values that make up the mechanical circuit, you would have a value here of P in. So we've got a value of P in that comes from the electric circuit here as the amount of watts that's provided to this motor, which now is going to be considered in its efficiency. So what does that mean when it comes to your P out value here in horsepower? That's going to be the result of a value of P losses added to the P in. So P losses are going to be, of course, a negative value. They're going to be a loss. So here's where we're going to put P loss in here as a real value. So now you've got a P in value in watts added on to a P loss value as a negative value. And what's that going to leave you with? That's going to leave you with a P out value here, right? So we know that P out equals P in plus minus P loss to give you P out, or you can say P out plus P loss equals P in. You get the idea, right? But what we need to understand is that that value there of P out is going to be used along with the efficiency in order to determine what we have over here. And what's that? That's our P in value, right? So if we were to actually look at this motor power triangle here, that means down here we're going to have, in terms of our power triangle, this is going to be our P in, right? So when we look at this in terms of the motor's values of power, real power, this is our P in value, right? So once we have our P in value, it'll be our efficiency, as we know and what we just looked at, that's going to determine our value of P out from this triangle. So that means if we look at our P loss, right, so this is going to be P loss. What we're going to be left with is our P out. So I don't know, I'm getting all kind of mucked up here, but that means what's going to be there is the remainder, which is P out. Okay? So I just wanted to kind of summarize that, and then the next thing we'll do is we'll get a question from the textbook, and we'll go through it using the numbers. So that's what we're going to do next. Okay, so here's where we're looking at the textbook question that I'm bringing up here next. And it's from the power section, chapter 17 of Robbins and Miller. And it's question number 26 that I'm looking at. So it says a motor with an efficiency of 0.87 supplies 10 horsepower to a load. It says its power factor is 0.65. It's a lagging power factor, like all motors are with their inductors and coils in their their AC load circuit part of the motor. And what is the power input to the motor? So that would be our P in value. And it says, what is the reactive power of the motor? Knowing that we have a lagging power factor, that reactive power is going to be QL vars. So we're going to be looking for QL vars. It wants us to draw the motor power triangle and ask what the S value is, or the apparent power of the motor. Now, we don't have all the information we need in the written part of the question. The rest of it is found down here in the figure 1750 as our diagram. So we can see from that we're connected to a 600 volt source at 60 hertz, and we have the details of the power output being 10 horsepower, our efficiency of 0.87, and remember for the textbook it indicates power factor as F sub P. So we've got F sub P, or our power factor, equal to 0.65 lag, and lag of course because it's inductor. Okay, so here's where we're going through an example of one of these questions that involves motor power factor and efficiency. And I'm picking up question 26 from Robbins and Miller. When I put this video together, I'll use screen capture to go to the question so you can see it and follow along with the way it's shown in the textbook and our solution here. But it goes like this. A motor with an efficiency of 87% supplies 10 horsepower to a load, and then it refers to a figure 1750 in the book, and it says its power factor is 0.65 lagging, and like all motors with its inductive coils and so on, we're going to be looking at lagging power factors from a motor. And so it says it's 0.65 lagging power factor. It wants us to give the P in value for the motor. So what is the power input to the motor? So P in, it's saying what is the reactive power to the motor, and of course because we're a lagging power factor, we know that reactive power is going to be QL, so those will be QL vars, so we're going to determine QL. It wants us to draw a power triangle, and it's asking what the apparent power, or the S value, is for the motor. So if you refer to the diagram, that's what I had to do here to get some of the details. But first of all, like it said, we have a 10 horsepower motor, so we know that's our P out value, right? So when it comes to here, this is our P out value of 10 horsepower. It said we had an 87% efficiency, so there I've indicated the efficiency is 0.87. Then we move on to the motor as the load in this electric circuit. The motor is being supplied by a 600 volt, 60 hertz source as per the diagram given in the textbook. And then it says we have our 0.65 lagging power factor. Okay, so first thing we're going to do is we're going to determine our P in value in our power triangle. That's going to come from our P out and our efficiency, right? Because remember, when we're looking at that value of P in the power triangle, it is a result of a P out value added on to your P losses to give you P in. This P out value, you know, is going to be your P in times your efficiency, right? So if we want to know our P in value, that's going to be our P out divided by your N value, or efficiency. So in this case, we're going to take our 10 horsepower and we're going to convert it to P out. So we know we've got 746 watts equals 1 horsepower. So that means 10 horsepower. 10 horsepower is going to be 7460 watts. Right? So we know that's our P out value, right? So when we look at our P out value, so we've got P out value here equal to 7,460 watts is our P out. So with our P out value and our efficiency, we can determine our overall P in here. So just so you kind of can relate to that, I showed all that. But what I'm going to do is I'm just going to now get rid of some of this clutter, and we realize that in our power triangle, we're working with the P in value, right? So we know we're working with the P in value. So P in is equal to P out divided by efficiency. So that's the thing we're going to do next. So I'm going to take my calculator and go 7,460 as my P out value. 7,460 watts, because we put it in watts, divided by 0.87 for the efficiency. So divided by 0.87 gives us 8575. So that means that our P in value is 8575 watts, right? Now we know we have a lagging power factor, right? So that means that we have a QL value, we have an S value, and we have an angle here that's going to indicate what our circuit phase angle is, and in turn can either give us the power factor, or we can use our power factor to determine that angle. So based on the fact we're looking for a power triangle here, let's complete that by now moving to the power factor to determine this angle theta, and we can use that power factor as well to determine S. So we'll just start with the angle here. So in order to come up with that angle, we know that theta equals the arc cos of 0.65, because this is our power factor, right? So we've got the arc cos 0.65, and that is 49.5 degrees. So that makes this 49.5 degrees in our power triangle. Number of different ways we could come up with S. We could take our P in value and divide it by our 0.65 to get that. or we can take the power factor and come up, and the angle, and come up with that. You can do it a number of different ways, but what I'll do is I'll simply come up with that S value by dividing the watts divided by power factor, right? So if I take the watts, 8575, and divide it by 0.65, that gives me 13,192, I'm going to say. So this is going to be 13 kVA, but I'm going to still express it as 13,192. Keep everything in units of VAs, watts, and bars. So 13,192 VA. And so that's going to give me my S value. Now, in order to come up with my QL, my final side, all I have to do is do a polar to rectangular conversion to get that, right? So what I'm going to do is 13,192 at an angle of 49.5, and then I will convert that to its rectangular form, of which we have, wait a second here, don't like the results there. My real power value is coming up somewhat different, so let me go back there. 8575 divided by 0.65. Yeah, maybe I probably need to go a little bit farther with that decimal place. 0.3 VA. So now I'll try that again. So 13,192.3 VA. 13,192.3 VA at angle of 49.5. Oh, I know, my angle at 49.5 was fairly rounded, so now we're going to convert that to, 8568 is what it ends up coming up there. So that's a pretty good difference there based on the rounding of that angle. So what we're going to do is just kind of tune this up a bit, guys. Second function, arc cos of 0.65 is 49.46. When you're working with larger values, you can see how these values being larger, and that degrees obviously makes sense, makes a lot of difference. So let's just go with 49.46 to help out with that. So then we're going to go with 13,192.3 at angle 49.46. And that's better. 8575 is what we get now. So a couple of decimal places on your angle. And now I'm just going to move to the value of QL here, which turns out to be 10,025. We're going to say 20. Yeah, we'll keep the decimal place. 5.5 bar. Okay, so that's our complete power triangle now. We've got our S value, we've got our angle to two decimal places here, indicating our circuit phase angle, which would be the lagging current in this circuit, right? Remember, I here would lag E source because this is a primarily inductive load when it comes to a motor, and Eli would have to be describing the voltage current relationship. That being the case, we know that in this case the current is lagging by 49.46 degrees. Okay, so then we've got all our values in our power triangle. So complete power triangle, we've got our QL value now because it came from our power triangle. We've got our P in value that was coming from our efficiency of our motor. And then lastly, we have our S value. So we got everything we required from our power triangle. Okay, so just bringing in the second part of this exercise where it involves question 27. So we're talking about the same motor circuit that we just went through, the one shown here in figure 1750. And it says to correct the circuit power factor to unity, so that's going to be a power factor of 1 when voltage and current are in phase, and our S value equals our watts, and we've got all true power dissipation. And in order to do that, we know we're going to use a correction capacitor connected right across the source in order to get rid of, if you want to call it that, get rid of the QL value in this power triangle and bring us to unity. And so it says show where the capacitor is connected, which we know is going to be right across the source or the load, depending on how you look at it, and determine its value in farads. So that's where we're going to be looking at a value of capacitance. So that's where we're going next here. And I don't think I solve it. I think I just go through the procedure there, and you can come up with the value. That's question 27. Okay, so lastly here, guys, working from that same question, question number 27 is relating to this same circuit, this same motor. And question number 27 says, to correct the circuit power factor of what we just did to unity, a correction capacitor is added. Show, first of all, it says show where the capacitor is connected. Now, I talked about this before. All power factor correction is connected right across the load, right? So it doesn't matter whether you show it here or here or here, but it's right across the load, it's right across the source. So it wouldn't matter if this was a series connection or a combination. All of the correction would occur as a correction capacitor right across the source. And being that it wants you to bring it to unity, it wants us to determine the value in farads here, right? So what is the value of F for that to bring this to unity? Well, all we have to do is look at the power triangle to come up with that. For us to be at unity, for PF to be at unity, we know that QL equals QC. So here's our QL value, right? We simply have to come up with a value of QC first, and then from there we can translate that to its C value, right? So when it comes to our QC value, we know QC is going to equal V squared, or E source, in this case 600 volts squared, divided by XC. So obviously if you want to come up with XC, that's going to be V squared over QC. Where do you get your V squared value? From 600 volts here. Where do you get your QC value? From your power triangle, of which you need to counteract your QL in order to give you QL equal to QC. Then once you have XC, you know that's amount of XC that you need there, and where that brings in 60 hertz now to calculate your C value from your XC equals 1 over omega C, right? So you can take it from there. For 60 hertz, omega is 377. So that should allow you to go about determining the results there, but that's really the procedure to go about this when you have a motor and its efficiency and then the power factor of the electric circuit. Remember, the motor is a load to the electric circuit and the source to the mechanical circuit, and that's where efficiency comes in, is to the mechanical circuit, and the losses involved in the friction and everything. That's a real loss in heat as a P loss value. So now, of course, you could have this question in a number of different ways, couldn't you? You could have a power factor of a motor with a VA value, all given, instead of having to calculate it, all given values, and then with the efficiency, you could be asked what the P out value is and so on. So, or you could be given the P out value in this and then asked to give the efficiency. So you kind of get the idea of the way all those values could be worded in a problem or a challenge. So hopefully that helps, and I'll get this all edited and published and put on D2L. Okay,